Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And within that playlist I have several little mini-series, and each one covers a different type of ANOVA design or model. In this little mini-series we're going to look at repeated measures, one-way fixed effects ANOVAs. And this is model development. And so the general development is this: a total of A measurements are taken on each of N subjects. Now technically it doesn't have to be subjects, it's just an object or an observation repeatedly taken measures upon. But my mindset somehow thinks it's easier to think of them as subjects, because then one subject receives those A different treatments. Now the A measurements correspond to the A treatments. Now, if the treatments are not time related, then the order in which the A treatments are administered to the subjects are random. And I'll point out what this means in a second. So the model in scalar form is y equals mu plus tau I plus beta j plus epsilon ij. And so this is the overall grand mean effect, and this is the treatment effect, and this is a subject effect. And this is just the error, fluctuating about our model. So the Yij is the response of the jth subject for treatment I. Now the mu and the tau 1 through tau a are fixed unknown parameters. The beta are considered random variables. And so we're taking a sample of subjects for this experimental design. We're assuming they're normally distributed with mean zero and they have some variance associated with them. The error term, Eij, is IID, normal zero, constant variance sigma squared. We're going to assume that the subject and the overall error are independent. This is for all I and j. And this is the general layout. So if we think of treatment down the left side, so treatment 1 through treatment A, and subject are the columns. So subject 1 receives the A treatments. Now, the order of treatments are random within this column. Now, one note, and so subject 2, subject N, they all receive A different treatments. Now, with two treatments, we use a paired t-test. So sometimes the treatments are before and after. And so you might ask, well, how do you randomize before and after treatment? Because before always has to come first. And that's what I meant by this piece here. So if the treatments are not time related, see, before and after is time related, so you can't randomize within that. So if they're not time related, then you randomize it. And again, if it were two treatments, then we can use a paired t-test, or this same procedure. It doesn't have to be a paired t-test, where you take the difference. So in matrix form, it's this. So y equals x beta plus epsilon. And I actually later added a star because within this beta parameter, I have mu's, taus, and betas, and I didn't want to confuse these betas with that beta, so I put a star there. Now the design matrix X has a column of ones associated with this grand mean, the mu parameter, and the part of the design matrix that corresponds to the treatment effects, tau 1 through tau a, we call X tau, and the X beta is associated with these. And hopefully this will make more sense in a second. So, but instead of carrying all these individual parameters, we usually use just vector notation. It just shortens up the notation. So mu, tau vector, beta vector, and those correspond to how many treatments or how many subjects we have. Now we could, when we do this multiplication here, we get this. So mu plus x tau plus, times tau plus x beta times beta plus error. Now here the betas, of course, or IID, normally distributed 0, mean, and variance covariance matrix sigma beta squared I. So it's just down the diagonal. The epsilons are normally distributed, mean 0, constant variance sigma squared. Covariances are 0, beta and epsilon are independent. Now to be a little more explicit in what the form of these look like. So if we have Y, these have to be, well, they don't have to be, but in order for the theory to be a little cleaner, you want to group them. So the first N observations are associated with treatment 1. And then we put the subjects in order, 1, 2, 3, 4, all the way to N. Then the next group of observations would be associated with treatment 2. And then we put them in order, subject 1 through subject N. And then, of course, the last N are associated with treatment A. And then we order the subjects from 1 to N. Now, the design matrix has a column of 1s, which, we represent it by the 1 vector. The part of the design matrix associated with the tau parameters we call x tau. And notice that it's just a vector of 1s, N of them. And the reason is because when we multiply this over, this column will only pick off treatment 1. And that's what we want for the first N. Now the second N, then this 1 vector goes to column 2. So when we do this multiplication, it picks off tau 2. And then all the way to the 8th column, right? Because there's A treatments, 1, 2, 3, all the way to A. And then X beta associated with the beta parameters. This is a little awkward, but the first N rows, this is the identity matrix. So it's a diagonal of 1s. And then it's repeated, diagonal of 1s, diagonal of 1s. And you can kind of see that if we take this multiplication, it picks off tau 1, and then we want it to pick off beta 1. And then the second observation, when we do this multiplication, again we're picking off tau 1, but we want it to pick off the second beta for the second subject. And so that's why it goes down diagonally. And then it just repeats. And so when we get to the 8th treatment, and we do this multiplication, this, of course, this 1 vector picks off mu. These pick off the tau A. And then these, as you go down, picks off beta 1, beta 2, beta 3, all the way to beta N. So this is the overall shape of the design matrix. And now, in the next few videos, we're going to look at the column space associated with this part of the design matrix, this part, and we need to start developing the projection matrices associated with the overall design matrix. But it turns out that it's easier to think of it in pieces, and all that will make more sense in parts 2 and 3. Of note, though, this mini-series is actually a brief introduction into repeated measurements and mixed models and block designs. And so the block designs will be the next mini-series after these 6 or 7 videos. And this particular design, the repeated measures, one-way fixed effects ANOVA, actually mirrors almost 100% the complete block designs with random blocks. And again, that's the next mini-series. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.